Hello and welcome to what I think is the first ever podcast from lifeupfront.com. I'm your host, Jeff Waters, the man behind lifeupfront.com. I recently caught a short, pretty intriguing post on Kenneth Wong's blog, The Virtual Desktop. It's a really cool blog, so check that out as well, relatively new. That's at Desktop Engineering. The article was about Dezineforce, which is a UK-based company looking to take FEA and CFD analysis into the clouds. And I asked my guest, Dezineforce's CEO, Dr. Peter Collins, if he could spend a little time discussing this new approach. Peter, thanks for joining me and welcome.
A pleasure to be with you, Jeff.
Well, as concisely as possible, let's start at the beginning. What is Dezineforce?
Dezineforce's mission is to compress design cycles and to enable designers to achieve better designs, be more confident about the quality of designs that they have achieved by enabling them to comprehensively search design spaces or scenario spaces in arriving at their design decisions. And how do we do that? We combine industry standard CAD and simulation applications with our proprietary suite of optimization tools, script those up using what we call workflows. We daisy chain the applications to run in batch mode on our high-performance compute clusters. But those workflows are kicked off, executed by the design engineer sitting at his desk, accessing our clusters through our portal. And as such, we are providing a third way between the traditional choice of complete control over your design process, but at the expense of having to have all of the IT infrastructure in-house, and handing over the design process to consultants in order not to have the IT platform in-house. With Dezineforce, you remain as the design engineer in complete control of the design process, but we look after the IT infrastructure and the software running on it.
So, I'm a huge fan of this software as a service movement, or SaaS, I suppose people call it, SaaS. I personally have been a long-time user of tools like Salesforce.com and NetSuite and, even things like Google Docs. So I think that, my love for those tools and my love for all things FEA and CFD, it just really, I find your concept intriguing. I remember something similar to this a few years ago. I think Fluent, I remember them maybe 5 or 6 years ago doing something called remote server credits. But I didn't really hear how they took off with that. And I don't hear about it today. Is this similar or in some way better than what they were doing?
We think it's rather different. Fluent continues to offer that service. And if your primary requirement is to execute single standalone solves remotely, that's still probably a very good option for people. Why we think what we're offering is very different is we're offering a solution to the design process as a whole. The design process needs to consist of very much more than just assessing the performance of a single design. But if simulation or analysis is to truly make an impact on design, the results of these analyses or simulations need to feed back, and they need to feed back through a process of evaluation of the various design options you've got, using optimization tools. One of the reasons there hasn't been a greater uptake of optimization tools is because they can be difficult to use both in themselves and in conjunction with simulation or analysis packages. So a lot of our focus has been not just on development of a comprehensive suite of optimization tools, but on integrating them with simulation or analysis, FEA or CFD or kinematics packages, in order to make the whole easy to use on a compute cluster.
So I, as I am learning more about your offerings, I think that's an important point. The actual solver engines are commercially available codes. and from that perspective, it's not really software as a service like a NetSuite or a Salesforce.com. With the exception of your own optimization software that you've written. I think that would probably fit the category. How do you select the tools that you're going to offer, the specific FEA and CFD tools?
In response to customer need. It was never any part of our vision to recreate what are perfectly good industry standard FEA, CFD, kinematics, etc. tools. It's our purpose in life to enable people to get much more out of their use of those by completing the cycle, completing the feedback back to the design. Now, so people have already chosen, for the most part, their FEA or CFD or kinematics or electromagnetic solver of choice. And it's we want to to enable them to build on that. They've already made commitments for the most part in terms of getting familiar with a particular solver or family of solvers. The time people take to train up on individual solvers is usually fairly considerable, and we're not trying to get them to ditch that investment, so to speak, but to build on their experience with that solver or suite of solvers by now taking on board optimization capability as well. So people will typically come to us and say, we already use Nastran, or we already use ANSYS, or we already use StarCD, or we already use Fluent. And we'll say, fine, let's build a workflow for you based around that solver, but with the optimization stages upstream and downstream in the process in addition.
So your customer then has a couple of different entry points into this customized workflow that you'll develop for them. If they don't have any analysis tools, you could work with them and they're sending you just pure geometry, and then it's more a responsibility of your engineers to do some of the meshing and model preparation. Or if someone is already using say Nastran and they use Patran as the front end, they might be able to feed you meshes from Patran if they really feel like they want to do that part of it.
The first comment I think I'd like to make in response is that the design engineer is himself uploading the what we would call the definition of design intent, whether that's a mesh or indeed it could be further upstream in the process, the output from a CAD engine. He or she is uploading that CAD file or that mesh and executing the workflow themselves without intervention from us unless that's required, because the customer's design data remains confidential to them unless they specifically want us to help them with the execution. Then, if they're already simulating, yes, they're simply using the same model, FEA or CFD or whatever model that that they would already have built at home base, so to speak, themselves. If they're not currently simulating, then we have a freer hand, so to speak, to advise them which solver might be most appropriate for the type of structural integrity check or aerodynamic simulation that they want to make. In such cases, we will call on consulting partners, Dezineforce's consulting partners, to help them build or build on their behalf the appropriate simulation model for submission to the service. Dezineforce we are not ourselves design consultants. We do not set out to have domain-specific design expertise. We're providing a platform for people, and we have optimization expertise. If people need help with domain-specific design or analysis, in other words, parameterizing a CAD model or setting up a model for FEA or CFD or kinematics or electromagnetic simulation, we call on our consulting partners to work with the service user.
Yeah. Oh, okay. Yeah, I think I was mistaken on that. So that makes sense. Your core value or offering is the expertise in designing the optimization workflow to minimize the number of runs that someone might need to achieve a particular outcome, for example, based on some algorithms that you've studied and that you understand, and also access to a level of compute power that a lot of people probably can't afford, certainly in small to mid-sized companies.
That captures it perfectly, Jeff.
I'll have to write for you. Okay, good. Yeah, let's talk about that for a second. Maybe just some metrics. I know I've seen quite a few in the old days Cray supercomputers lined up in larger companies that were involved with FEA and CFD. Computer horsepower has gotten amazingly fast in the last decade, and people are even finding ways to do relatively inexpensive cluster computing with fairly normal hardware from Dell, for example, networked together. But that's still an investment, and there's still, it's not easy. It's not just plug and play. You're going to have some IT staff devoted to supporting that. These are the typical advantages of software as a service in any case, but what kind of a speed up are we talking about just in solution performance? Is there any way to sort of give us an idea of that?
Well, what we are focused on is reducing the overall design cycle time, the time taken to arrive at a design decision. And typically, certainly recent experience with some of our customers suggests that the kind of average reductions in design cycle time range from a year to 3 months, or if 3 months would previously have been the design cycle time, down to between 2 and 4 weeks. So typically you're talking about compressing the overall design cycle time by roughly a factor of 4. Now, within that, if anything, we encourage people to take a little more time than they may previously have done to think about what their design objective is, to think about what are the degrees of freedom that they have in improving that design, what are the parameters that they can vary and within what ranges, and to identify clearly what the constraints are. Then the time to set up a model to simulate the performance in structure or aerodynamic or whatever terms will be much the same will be exactly the same in using this service as if you're doing the simulations under your desk. Where the big time saving kicks in is between having set up a model to simulate the performance of your initial design intent and receiving back a complete picture of the performance of all of the design options that are available to you within your design space, or the performance of an individual design across the range of operating conditions to which it might be subjected. And that speed up is coming from 3 factors. One, the fact that you can run individual solves on a number of ways parallel. And that can be 2, 4, 8, 16, 32 ways parallel. Now, the degree of parallelism in execution of individual solves that makes sense to minimize the turnaround time for individual solves is a function of things like the mesh size, the nonlinearity of the physics involved, and, for example, whether the analysis is steady state or transient. So the degree of parallelism is very, very appropriate. Parallelism is very case specific, but at least with access to a high performance compute cluster, you can select the optimum degree of parallelism to minimize the turnaround time of individual solves. Secondly, with the high performance compute cluster, you're then able to execute a number of solves in parallel. on top of the fact that the individual solves are being executed in parallel. Next, you're reducing the number of solves that you actually need to characterize a design space or a scenario space comprehensively by use of design of experiment methods. And we can go into that in a little more detail if you wish in a little later.
Actually, let me jump in there, Peter. So, we had a previous conversation and you were kind of explaining some of the real high-end methods that you've written into your algorithms. This is your software, not the commercial software that you use for the analysis, but your software for really helping people to decide what they need to pick from a large design of experiments. So if you look at a huge matrix of design of experiments very quickly, depending on how many variables you need to look at, it might traditionally say, okay, we need to do 50,000 individual runs. But with your algorithms, you're able to somehow look at a sensitivity study in 3D space and decide, okay, really we need to focus on just these few, so maybe we get that 50,000 down to 100.
Quite. That's a typical, that's indicative of the degree of reduction achievable. What you're doing is the design space is made up of the parameters whose value you can vary in improving the design, and the ranges of the values of each of those parameters. Now, if you talk about varying only a single parameter in your design space or scenario space, and you might need typically 5 to 10 FEA or CFD solves to characterize the performance of your design. If it's 5 to 10 you need when varying a single parameter, that suggests you need between 25 and 100 in varying two parameters simultaneously, 125 to 1,000 in varying 3, and so on. Or put another way, the number of, if you simply march through the design space and simulate the performance of every design variant in that space in a linear fashion, the number of solves you need goes up to the power of the number of parameters in your design space, the number of parameters that you're simultaneously varying. And once you get beyond 3 or 4 parameters, it simply becomes intractable. We've had a recent request last week from a wind turbine manufacturer who wanted to know if we had a better solution than the 400,000 solves they thought they were looking at to characterize the various design options open to them, because they reckoned it was going to take them about a year. And that's on a very high performance compute cluster. With the so-called sparse methods, which underpin our design of experiment approach, you can select, with the help of mathematical algorithms, a representative set of points within that design space, much more sparsely than without the help of those algorithms. So that typically the number of points at which you need to execute solves goes up linearly with the number of dimensions in your space, rather than to the power of the number of dimensions. So 5 to 10 becomes 10 to 20, becomes 15 to 30, and so on. And so yes, you're talking about a few tens to a few hundred solves to initially characterize the performance of your design, as opposed to hundreds to tens of thousands. And that obviously dramatically reduces the overall time that you need to characterize the performance of your design across the design space. The final element of the compression of the design cycle arises from eliminating the need for designer intervention once he or she has defined the initial design in terms of either the output of a CAD engine or a model, a mesh. because once that's done with design of experiment methods, you generate the workflow will call for the generation of the variance on that design across the design space, and call automatically for the solves at each of those points. And in the course of that, do the pre and post processing all in batch mode, so that you basically perform the sweep across your design space without the designer having to do the pre and post processing one solve at a time. It's that iterative or batch mode execution that means you're not waiting for the result of one simulation to decide, okay, shucks, that means I need to change my design by this much, and now I'm going to resolve, and then I'm going because that linear progression with the need for the designer intervention each time is a key element of why design cycles take as long as they do. We'd also suggest that what that's doing is focusing quite a high proportion of the designer's time on what boxes actually do better, which is the repetitive task or set of tasks involved in pre- and post-processing, and means he has less time to do what designers do much better than any computers, which is exercising judgment, thinking about their objectives and thinking about their constraints up front, and interpreting the results and making design decisions once the boxes have come back with the results of the analysis. And a part of what we're about is, in effect, redistributing, there's a redivision of labor, with the designer spending his time thinking, exercising judgment, exploiting drawing on his experience, and focusing the boxes on the repetitive tasks. Because boxes don't get bored with repetitive tasks, they don't screw them up.
One point I want to make, and this might be just a cultural difference in terminology. Here in the States, when you use the term designer in industry, generally we're talking about someone who is a CAD jockey or a CAD user. They're doing detailed design. Not necessarily, they don't necessarily have a 4-year mechanical engineering degree either. And then there's a little bit of a spread with the term design engineer, where you may have a little mix of both, but typically they're still more focused on CAD. When you say designer, you mean what we might call more of an analyst with an advanced degree?
I guess some of the time I'm consciously blurring the distinction, and sometimes I'm just forgetting to be as careful as I probably should be, because in Europe as well as in the States, designer as often as not means the chap who's drawing up the design with the aid of a CAD tool, defining the initial design, and the analyst is the one using the FEA or the CFD or whatever analysis tool to assess the performance. To the extent that I sometimes blur the distinction deliberately, it's because I come back again to this integration of the design, simulate, evaluate process on the cluster to make it possible to run a complete process. In part of what we're trying to do is facilitate the dialogue between the designer and the analyst, using designer and analyst in the sense of which you've defined them, because there is we get a little bit frustrated by the pissing contests, if you forgive the language, that sometimes go on between designers and analysts, and amongst other things, what it tends to do is slow down a design cycle further, and a lot of the company's design experience doesn't necessarily find full expression if there's mutual incomprehension between the designers and the analysts. And to the extent that we can facilitate the dialogue by making the by improving the process integration, we think that we can enable companies to leverage the know-how of both the designers and the analysts to much greater effect. It's often designers who have the best experience of how to parameterize a problem, for example. Very often more so than the analysts. And yet, parameterization of a problem is key in as the basis for performing a systematic search through all of the design options available to you, or through the performance of a single design under a range of operating conditions. And so the contribution of the designer to this overall process can, and we rather think should, extend beyond just quote unquote defining the problem initially, or defining the design initially.
As I think about the process and envision it happening in real life, I can imagine what I typically see, at least here in the States, when you have analysts that are master's or PhD level users of these FEA and CFD tools. They will most often run a very few set of runs. They'll have a design of experiments, but they'll still end up only doing 4 or 5 analyses instead of the 400 that might be called for, simply based on the amount of time available to them.
Right.
And so they have to make some hard decisions, and that's what they do. And from that perspective, very often, they are not doing an optimized solution. So it's not an automated batch optimization process. Typically, usually, if you're just doing 1, 2, or 3, or 4, you can afford to spend a little bit of extra time doing the manual setup just to do them as one-off analyses. Now, with your process, if ultimately you're trying to get to this goal of taking, the 100,000 different design iterations that you ought to be looking at, down selecting that to the 10 with a very sophisticated algorithm, and then, or maybe it's 100 or 1,000 still.
It would be if it's 100,000 without the support of algorithms, it's probably of the order of hundreds with the support of DOE algorithms, yes.
Okay, so, and even that would be impossible to do if you had to do them one-off as an individual.
Exactly.
So if you can batch process those, now the challenge, it would seem to me, becomes how do you make a model that will handle these changes in parameters without blowing up to support that optimization process?
We definitely would say that if people have not taken a parametric approach at all, that taking a parametric approach will involve relatively more time. We would suggest that upfront investment is very worthwhile, because by then enabling a sweep through the design options available to you, you're identifying potentially problematic designs at a much earlier stage in the overall design and manufacture process. And it's this elimination of what I call latent design cycle changes, or left shifting within the process, as was described back to me by a customer the day before yesterday, is a way to take out a lot. It's a way to avoid the costs of having to make last-minute changes to design because prototypes are built and it's suddenly discovered that they don't perform well, for example, under certain operating conditions. Because it's at that point in the design cycle, once architectures have been committed to, for example, that making changes to design are particularly costly. So if you will, a stitch in time saves 9. That some early hard thinking to parameterize the problem, to identify what constitutes a better design? In other words, what's our objective here? And what are all of the constraints that we're under, because sometimes the analysts come back and don't realize until they come back with their results that they get told, yes, but there is this additional constraint. And just the putting sufficient structure on the process that these conversations are happening up front between the analysts and the designers before the compute cluster is told to go fetch, clarifies and generates a level of common understanding, which in our experience pays rich dividends.
Yeah, well, I appreciate you spending the time with us. I've actually learned something on this call as well. I think I had positioned your offerings a little incorrectly in my mind. So again, I was thinking really this was more about the cloud computing. That's actually a smaller element, and it's not truly cloud computing in the sense that people typically describe cloud computing. So you have word processors and image editors, and spreadsheets are now online. They're they're applications that run wholly online. That's not what we're talking about here, although there have often been these discussions, when will CAD and CAE become wholly online ASP model applications? Is that something that you see in the near future? If you had a crystal ball, what's our direction there?
I think we're perhaps a little way away yet from the kinds of web or over-the-web response times to, for example, 3D manipulation, which involves very high rates of data transfer in very high speeds, or requires very high speeds of data transfer to give people the kind of response that they've come to expect. So that's at least one practical consideration. I think you may find that the short-term focus we certainly think that where we can deliver the greatest value, at least in the immediate future, is by taking away from people the grief of the building and managing high-performance compute clusters. We don't typically tend to find people complaining terribly much about CAD tools having to run locally. It's part of the whole cloud computing proposition is taking away the grief of the platform in-house. While in the engineering design space, the biggest source of grief tends to be that cluster, either the lack of one or when you've got one, maintaining it and scheduling jobs across it. And so it's from a pure delivery model perspective, our focus has been very much on the pain point of the computationally intensive large number of solves and the platform to run them on. But I guess where we're also a little different from many other cloud computing applications is that our focus on the increment, which is the optimization, and on the integration of that with the stages further up the design process. So the integration of the simulation and the optimization to make the whole run more easily. So in that sense, I guess we're more content rich than, for example, a Salesforce.com or a Microsoft Office in the cloud.
I see. Well, Peter, I can't thank you enough for the discussion today. How can my readers find out more about Dezineforce? What's the best way to learn about your offerings?
We would be equally pleased to hear from you via www.dezineforce.com, and that's spelled DEZ or DEZINEFORCE.com. We find live chat a wonderful way to communicate with many of both our prospective users and our actual customers. Or please do call us. And the fact that this conversation is happening in the afternoon Boston time is indicative of the fact that we're actually very used to interacting with people live at times of the day that suit them, irrespective of what time zone they're in.
Correct. It's about 4 p.m. here, 9 p.m. for you?
9 p.m. We love what we do. And so, yes, that means we work different members of the team work different hours, but that's because we passionately believe that we can enable people to do design better, to do it more efficiently and get to better answers. And we get such a kick out of the difference that people have been able to achieve working this way that we're very happy to interact with them then at a time that suits them.
Great. Well, thanks again. I really appreciate it.
Thank you, Jeff, very much. Very much appreciate your interest.
All right. Our first ever podcast is in the bag. For more info on CAE trends and best practices, please visit my blog at lifeupfront.com. And I'll put some links to Dezineforce in the show notes and welcome your comments. Now, go be productive.